Welcome to module 4 of this course, Ultrafast Optics and Spectroscopy. In this module, we will study dispersion effects which is experienced by ultrafast pulse while propagating through the dielectric medium. We have already mentioned that when ultrafast pulse propagates through a medium, it experiences two effects. The first one we have already studied, high intensity effect, which is collectively called nonlinear optical effects, and the second effect experienced by the pulse while propagating in dielectric medium is large bandwidth effect, which is called dispersion effect. In this module, we shall learn dispersion effects experienced by an ultrafast pulse when it propagating through a dielectric medium. Material dispersion always stretches a pulse in time, and that's why a short pulse here, the pulse duration is expressed by delta t before propagating through the medium, and this delta t time duration of the pulse is defined as the full width half max of the intensity profile, which will become larger as it propagates through the medium. This is delta t after dispersion, and that is unavoidable for any dielectric medium. So, this is the topic of the present module. But what is dispersion, by the way? Dispersion is a variation of refractive index as a function of frequency, which is shown here in this figure. We see that in the visible regime and UV regime or IR regime, where most of the spectroscopies are performed, refractive index of the medium is much higher than 1. Refractive index of the medium in IR and visible or UV regime, they are greater than 1, but in the X-ray regime, the medium dispersion becomes less than 1, and there is a consequence for it. We will go over the consequences later, but one thing we should note here, that in the normal dispersion regime, refractive index always increases as a function of frequency. This has two important effects in light propagation. The first effect is temporal effect, and the second effect is spatial effect. In temporal effect, we have already come to know that phase velocity depends on refractive index Vp. It depends on refractive index, and refractive index depends on frequency. That's why phase velocity of red light low frequency component would be much higher than phase velocity of the blue light. That's why if I have a combination of red, blue and yellow lights, they are propagating in vacuum, and once it's propagating through the medium, a dispersive medium, then we see that red light propagates at faster velocity than the blue light. So, this is the temporal effect we see, which means that if I take this analogy and then try to understand what might happen to the ultrafast pulse, one can think of like this way. I have a red and blue components in the vacuum, they are propagating, but the moment it is propagating through the medium, what will happen? this red component would travel at a faster velocity than blue component, and slowly I am stretching the pulse, and this effect is unavoidable effect for any medium. We will calculate how much stretching we will experience very soon. Another effect, dispersion effect, is spatial effect. According to Snell's law, when light propagates across an interface, angle of refraction is inversely proportional to the refractive index of the material or medium. And this inverse relationship suggests that if light propagates from low refractive index material to high index material, higher frequency light bends more, as illustrated here. So, blue light will bend more than red light. And we will find out what are the effects one can anticipate for the ultrafast pulse when ultrafast pulse is propagating through the medium. An ultrafast pulse carries a number of frequency components that we have already seen. We have represented ultrafast pulse, and the representation was following. We can remind ourselves. We have represented the electric field in time domain as AT multiplied by e to the power I omega naught t minus k naught z. This part is carrier wave part, oscillatory part, and this part is field envelope. And then we get the intensity, which is nothing but AT square modulus. And when you express intensity of an ultrafast pulse, assuming a Gaussian pulse like this, that is centered at t equals 0. The moment I do Fourier transform of this time domain pulse, I get a frequency domain description of the field, and we suggest that the frequency domain field is centered at omega naught equals at center omega naught. So, frequency domain field is centered at omega naught, and it has a bandwidth delta omega. So, when an ultrafast pulse propagates through a dispersive material, it will experience both temporal and spatial effects due to dispersion. In every ultrafast optical spectroscopy lab, different optics such as lens, polarizer, nonlinear crystals are used, and when ultrafast pulse propagates through these optics, it experiences dispersion. Effect of dispersion on propagation of ultrafast pulse is unavoidable because every medium exhibits some extent of dispersion. Effect of dispersion cannot be realized with time domain description of the pulse. It can only be realized in frequency domain description of the pulse, and that is why to understand the dispersion effects, we will express time domain pulse. Here we have taken a Gaussian pulse in frequency domain by Fourier transform. The transform limited Gaussian pulse is expressed by E naught e to the power minus AT square, that is the field envelope, Gaussian field envelope, and this is the carrier wave. Once we get the Fourier transform done, then we get this equation, this expression for field in the frequency domain. This expression shows that in the frequency domain we get another Gaussian envelope, and this is spectral phase. a phase factor which comes in frequency domain. That's why it's called spectral phase. Now this equation is valid when a pulse propagates in vacuum. That's why k naught is constant. It's not varying, it's not changing. In a dispersive medium, however, magnitude of wave vector must take more general form k omega. Consequently, spectral phase of the pulse is controlled by k omega z, this term. So instead of k naught z, we have to consider k omega z. K is a function of omega. And the moment we do that, we can express it in Taylor series expansion, because the k omega naught value is known, which is the vacuum value, and we have to expand this function around omega. That's why we can use this Taylor series expansion. The moment we look at the Taylor series expansion, we get the spectral phase description, which includes vacuum contribution k naught L, that is the L distance. So instead of Z, we are considering L. And the first term, which exists for plane wave as well, is the natural phase advance due to propagation through L distance, k naught L. So if we look at the expression for frequency domain field, it looks like this multiplied by e to the power I phi omega. Now, second term which we get is related to group velocity, the velocity of the envelope function. We remind ourselves, in a pulse I have two components, envelope and the carrier wave. Envelope is this one, and the carrier wave, which is the oscillatory part. And in vacuum, they travel when their phases are locked, like this way. And we said that there are two different velocities: phase velocity, the velocity of the carrier wave, and group velocity, velocity of the envelope. So group velocity is expressed by this d omega dk, which exists in pulse only. And the third term here is related to variation of group velocity as a function of frequency. So just little modification of this equation, simple modification by introducing group velocity, we get this term in the second order spectral phase. So this is your second order spectral phase. Second order spectral phase. In the second order spectral phase, we get this group velocity dispersion. This is the definition we are giving based on Taylor series expansion. Now, when a pulse propagates through a dispersive medium, additional phase is added to the propagating pulse, because in addition to k naught L, we start getting all these terms, and I can have even higher order terms as well, depending on the level of dispersion we have. Level of dispersion an ultrafast pulse experiences while propagating through the medium decides how many terms in this equation we should consider. This undoubtedly depends on the experimental conditions. However, to understand the influence of each term on the propagation of an ultrafast pulse, one can think of adding systematically each term and subsequently check the effects. If only the first term in the equation is introduced, that means this one, the pulse does not experience any dispersion at all. It's just like vacuum propagation. This is true for the vacuum propagation. In order to see the dispersion effect, we should introduce at least first two terms. That means these two terms we have to introduce to get the dispersion effect. So the first task would be, we will introduce these two terms, the first two terms, and then we will plug that in the frequency domain field, which was obtained previously, pi by a e to the power minus omega naught square divided by 4a multiplied by e to the power minus I. Then instead of k naught, now I have to write down k naught plus omega minus omega naught divided by Vg z. So this was the expression for the field in frequency domain. If we consider the first two terms, and then all we need to do is we have to convert it to time domain by inverse Fourier transform. In this, we will consider a new variable omega bar. So this integration will be performed with omega bar as variable, and omega bar is defined as omega minus omega naught. That just simplifies the problem. And then we get this expression in time domain. And now if we define another term, group delay, which is nothing but L by Vg. This L by Vg or Z by Vg we have here, we are giving another definition to this term. Here GD, group delay, is defined as L by Vg. This equation represents the outgoing pulse in time domain after experiencing first two terms due to dispersion. And L by Vg, distance divided by velocity, is nothing but time. That's why it is called group delay. What does it mean by this delay? I will just talk about it, but this is the way definition is coming. And final expression for the outgoing pulse after experiencing the, so I have an medium, a pulse is propagating through the medium, and we have assumed that medium is giving me only this dispersion effects. So it is called first order diffraction effects is included. What does it mean by this delay? We have already seen that optical pulse is synthesized by interference of electromagnetic waves with slightly different frequency, propagating along the same direction. And due to that interference, so I have a number of frequency components. This is one, second frequency components, then third frequency component, and due to the interference, we see that at this point of time we get constructive interference, and that's why pulse looks like this. This is the resultant electric field, how it's changing. And we have also seen that a pulse has two velocities, phase velocity and group velocity. Phase velocity is defined by Vp. Phase velocity is the velocity of the carrier wave, which is defined by omega average by k average, and group velocity is defined by d omega dk. These are the definitions we have already found in module 2. Now, in any dielectric medium, dispersion relationship can be written as k equals omega n by c. This also we have found previously. If we take the first derivative of k with respect to omega to obtain group velocity, then we get this expression, simple math. And then if we insert refractive index definition, that is the speed of light in vacuum and the speed in the medium, then finally we get an expression which connects Vg and Vp, phase velocity and group velocity, and we are trying to find out what is the relationship between phase velocity and group velocity in a medium. Because dn d omega, that is the slope, this dn d omega, and we have already shown that in non-absorbing regime, refractive index will always increase with respect to omega, which means that the slope would be always positive. Because slope is positive, omega is positive, n is positive in this equation, omega is positive, n is positive, Vg would be always less than Vp. Therefore, in non-absorbing medium, relative phase of envelope and carrier wave changes due to phase and group velocity mismatch. And that is demonstrated in this figure. If you look at the tip of the envelope and tip of the carrier wave, then we find that in the first pulse they are at the same time, but in the second pulse, as it propagates through the medium, the tip of the envelope and tip of the carrier wave, they are separated in time. It shows a mismatch. Again, it's further separated as it propagates through the medium. So Vg is always less than Vp in the medium, and that is representing the group delay which we discussed in the previous slide. Now, if we assume that due to propagation of pulse through a medium, only additional phase which is introduced is due to group velocity dispersion. Previously we have included group velocity only, now we are including second order spectral phase. Similarly, we are representing electric field in the frequency domain, and the spectral phase we have taken second order spectral phase, and we are now defining another term GDD. GDD is nothing but this term which we obtained from this equation, is just a definition, group delay dispersion. And here we remind ourselves that GVD is defined by this. This definition again comes from the Taylor series expansion. So with this GDD definition we solve, and then we do we get the time domain field by inverse Fourier transform, and taking the full width half max. So once we get the field in time domain, we can get intensity in the time domain. From field to intensity, we know how to do that. And then once we get the intensity, we can take the definition of full width half max of the intensity to get the width, because we are finally interested in the width, and we get an equation, a very simple equation, this one. What does it mean? Here delta T sharp, we have to remember that any time for a given spectral bandwidth, if number of frequency components are fixed, then anytime we are trying to broaden a pulse, it means we are introducing a chirp. So dispersion will always broaden a pulse, that's why we are introducing chirp. So we are defining this pulse to be chirp pulse, and the delta T is the intensity full width half max of this pulse. On the other hand, delta T G is before dispersion, this one. Again, this is also intensity full width half max, and this equation shows how this pulse duration and this pulse duration are related. It suggests that as we increase GDD, we'll have broader pulse. As already stated earlier, that dispersive pulse broadening is unavoidable in any optical medium because all optical material exhibits positive GVD. And how do we know it's positive GVD? We know from this equation, we know the definition of GVD. This definition is coming from Taylor series expansion, where Vg is expressed like this, and then we can calculate GVD. We get this expression. In this expression again we have first derivative and second derivative. We have to remember that refractive index increases as a function of frequency in non-absorbing medium, non-absorbing regime. That's why these terms are all positive. That makes GVD always positive. So we'll get a positive GVD from every material. And due to this positive GVD, the pulse will always broaden in time. It will be stretched in time. So it is desirable that we find out an optical material which features negative GVD as well, because we have to compensate the pulse. For some reason, if the pulse is propagating through a dispersive medium, it will always broaden and chirp will be introduced. So I need another medium which will introduce negative GVD to get my broadened pulse back to the compressed pulse. This table shows GDD, which is always positive, and it suggests that the unit of this GDD is suggesting that femtosecond squared divided by mm. So per millimeter propagation of the pulse, it will introduce this amount of GDD, and if we plug that in, we'll be able to find out what would be the final pulse duration after the propagation. Now, as I told you that dispersive pulse broadening is unavoidable, and in experiments there are many optics, there are many transmission optics which we use. That's why pulse will always broaden, and we need a material which will recompress the pulse introducing negative GVD. Unfortunately, there is no material directly can introduce negative GVD. Prism and gratings are two optical elements which are capable to introduce negative GVD by means of angular dispersion. So here we have to use angular dispersion effect to introduce GVD. To understand this angular dispersion and its effect on in producing negative GVD, let us assume the center frequency component of the pulse travels along z direction here, and k is the direction of any other frequency component. So, this is k and center frequency is propagating omega naught propagating along z direction. A prism, we know that light will bend due to angular dispersion, and one can write down the spectral phase. If we recollect, omega E omega, that is the field in frequency domain, is expressed as A omega minus omega naught, that is the envelope function, and there is a spectral component. The spectral phase is expressed as k is a dot product of k and z, which gives me k z omega k z cos theta, and k can be expressed in terms of omega by c n, that is dispersion relationship. So, finally, we get this spectral phase, and we are interested in second order spectral phase because that is introducing positive GVD in material. So, we want to find out, can we get negative GVD from the second order spectral phase. So, when we take the second derivative with respect to omega, we get this expression, and if we assume that theta angular dispersion is very small, this theta with respect to omega naught center frequency is very small, then sin theta can be approximately considered to be 0 and cos theta can approximately be considered as 1, and we can reduce this second order spectral phase. What we find is that a negative signature, a negative sign. Presence of this negative sign shows that negative GVD is possible to achieve with the help of prism or grating. So, in the end, let us say I have a short pulse, I have many mediums through which light is propagating, the pulse is propagating, and due to this propagation, in the end I get a broad pulse, a sharp pulse as well. It has to be sharp, otherwise we couldn't broad the pulse. Now, with the help of this negative GVD, all material will produce positive GVD. These are actually positive GVD. With the help of negative GVD, which is achieved by not by any material but angular dispersion, we may compress the pulse again. There is enormous application of this negative GVD in the construction of ultra fast pulses. We will study that very soon. So, with this we have come to the end of this module. In this module we have studied group velocity dispersion, meaning of positive GVD, meaning of negative GVD, how to achieve negative GVD. We will meet again in the next module.